Assalamualaikum warahmatullahi wabarakatuh, and a very good morning.
Waalaikumsalam warahmatullah.
All right. Okay. Yeah, very good. Okay. So today we're going to continue our class on a new chapter, right? So quite low attendance today. So maybe today is a very nice rainy day. So most of you still asleep, but don't worry. The rest can watch the recorded video later. Okay, so let's start. Before that, so it's better to revise what we have covered so far. Okay, so this is actually what is a DSP all about. So we are actually learning based on this thing, which is what we call the LTI system. Okay, so we started with a general system on week 1 and week 2, and then starting from week 3 onwards. So we are actually we are focusing on a linear and time invariant system. And so we are actually just solving a filtering problems. Okay, so there are other problems, but we are actually just covering that. But actually filtering is covering a lot of application already. Okay, so that's including the one which I already mentioned on example is on detecting faces, right? So actually that one is involving a filtering. And most of the deep learning algorithm that we have today, so if you know what is a deep learning, so it is an AI algorithm. So that one is a much actually relying on LTI system filtering. Okay, at the back, it is actually LTI system filtering. So okay, so that's actually the things, and actually we covered on first week. So how to convert from a continuous signal into a discrete time signal. Okay, the one which is discrete here is the time. Right. So what is a sampling? Sampling in time domain is actually we are converting the time into a discrete value. So which is t can be from 0 up to something, and we can have a floating point. 0.1 second, 0.0005 second, those kind of thing. But n, it is always an integer value. So your time will be 0, 1, 2, 3. Why is that? Because it is based on sample. Okay, so it's not based on second anymore. But whatever it is, you can convert it back from n to t. So there's a formula. So this is a formula. So what is the t? T is actually equals to n over fs, where fs is the frequency sampling. Okay, so that's the relationship. So but when we plot discrete time signal, so the x-axis is actually sample, and you can always convert that n into t based on this equation. Okay, so that's the first week, and then a second week. So we have seen a general concept on a system. Okay, so and then this is then we know that for LTI system you should have input, do something, do the filtering, you will get the output, and to do that you need a filter. Okay, so you need a filter because this is a filtering process. And other than filtering, so this is actually just a coefficient, system coefficient. Just because this is, we are looking into a filtering application, so we call it filter. Okay, so if in general, so we just call it system coefficient. Okay, so we have two types of coefficient. So we have a coefficient A. So this is a coefficient A and coefficient B. And we have seen that to do that, how to do the filtering. So either by convolution, okay, if it is FIR, finite impulse response, if your system is finite impulse response. So you can do convolution. But if your system is infinite impulse response, so you cannot do convolution because you cannot do convolution on infinite length sequence. So you need to solve the original difference equation. So what is the difference equation? A relationship between input and output. So you have input, output, and what are the processes to get the output? Okay, so to do that, so we have a basic here, input signal, output signal, and filter. And then we have looked into several analysis there are three approach on doing this analysis. What kind of analysis? So we are checking stability and causality. Okay, two things. Stability and causality is very important because if your system is not stable, so you cannot implement it. If your system is not causal, so you cannot implement online system. Online system means your input data is feeding live. Okay, once you are running your system, the input is coming into your system live. So that's what we call an online system. Can you do a non-causal system? Yes, that's where we when we implement offline system. So what is an offline system? So your input has been recorded. Okay, so you record everything first, and then you do the processing. Okay, what is the example? Example is you capture an image. You capture an image, and then you do the processing later. Okay, so online is something like you have a video feed. So you have a video feed. You are processing the video feeds live. Okay, so that's an online system. So the same thing if you have an ECG signal, because maybe most of the time what you do is you record the ECG signal first. Okay, record everything. After maybe you get 10 samples or maybe 20 samples, and then later you do the processing. You do the filtering and everything later. That case, you can do non-causal. Okay, so you can do the non-causal. So if not, yes?
I would like to explore this causal and non-causal because the concept is hard to grasp, if you don't mind.
Pardon? I cannot clearly hear you.
I don't really understand this causal and causal system, and I would like to ask further if you don't mind, or would you prefer me asking later after class?
You can ask now, no problem, because we are sharing the knowledge.
Okay.
So do you
So
have a specific question?
the causal and non-causal, as the name suggests, does it mean that live signals have a effect when we measure it? Does it have a we call that a cause?
Is there any difference on the outputs,
Yeah.
whether we do it online or offline?
Because what do you mean by online and offline, doctor?
So online means live feeding of input data. So live feeding is like when you take an ECG signal, you measure it while you are measuring it on a person. Okay, you put a sensor, some nodes on the patient body or the person, right? And then the data is coming in. While the data is coming in, you do the process. Okay, you are filtering the data while the input is coming in. Okay, on the spot. That's what we call online. Offline, you don't do any processing. You just collect data. Don't do anything to the data. So it is like it's a raw data. Okay, just collect it, record it, and then okay, store it somewhere. Store it in your storage, some memory. And then after that, you do the processing.
But
So
doctor, if we like record it first and then we analyze it later, how is it different than if we just live? Because the input signal will still be the same, right?
yes.
Live or not live.
Either it is live or not live. So that is why in so that causality is only important if you are considering online system. Okay, but is it going to give you a different output? I think
Yeah,
that is your question.
I think so, yeah.
Okay, so the signal is the same. It's just either you do it now or you do it later.
Yeah.
So actually, when we design, we need to make sure the output it is exactly the same. Either you do it online or offline. That's what we need to make sure. And one of it is, so when we have LTI system, so this is one of it. To make sure the output is the same, you should have LTI system because it is linear, it is time invariant. So what is a linear and time invariant? Time invariant, the output doesn't affected by the time you are recording. Okay, so that is actually time invariant. So it doesn't matter you do offline or online, you do it now or you do it later, the output should be the same. What is the linearity? Linearity is whether you are collecting the data at once or you're doing it, let's say, part by part. All right, so you should get the same. You should get the same output. So that's what we do on a test A and test B. So you have a two signal, plus it first, you sum the signal first and then do the process, or you split, do separately, and then a sum at the end. So you got the same thing. So that's linear. So that's why LTI system is very, very important, so that we can control this kind of thing. We can control this kind of thing. Causality is just, are you going to do it live or offline? So if your system is live, you need to know the output while you are checking the feeding, the input. So you need to have a causal system. It is a must. Okay. But if not, then you have a choice. You can have a causal or non-causal system. No problem. But stability, you need to make sure that any system is stable. Okay. So, and for stability, so this is why we have done some testing in Z domain. Let's see what is the Z domain. Stability unit circle must be inside the ROC. And we have seen, if you are if you all remember, FIR system. FIR system is actually the ROC is the whole Z domain, except either 0 or infinity. So what does that mean? The unit circle is always inside the ROC for FIR system. Okay, so that's another consideration. So if you doesn't want to get some headache, so consider FIR system. No stability issue. There's no stability issue. Stability issue is only for IIR. Okay, because we already know that unit circle is always inside the ROC. Okay, so that's what we have learned. So when you are designing a system, so so that actually most of the design filter, even for these the face recognition, identification, the deep learning things, the ECG filter. Actually, most implementation is using FIR. Okay, because that's the safest filter that we can have. No stability issue. Causality, non-causality, if we are doing it as a recording, so there's no problem either it is a causal or not causal. Okay, so that's why it is very important to analyze the system, to know that the system, is it stable or not stable, causal or not causal. Okay, and what we have covered is we can check stability and causality by three methods. You can look at the different equation, you can look into the impulse response, and you can look into the ROC. Okay, is that clear? So that's how you consider a system for implementation.
Clear, Doctor. Thank you so much for the explanation.
And we have covered so far until chapter 5 and 6, where we do inverse Z transform previously. So what we're going to cover next is most of it is on this blue box. So what we call a spectral analysis. So this is a different type of analysis. So we have done on checking stability and causality. Okay, so we have done on that. So we're not going to check stability and causality anymore. So we're going to move on. We're going to do a spectral analysis. So which is maybe a more important. Okay, so when we say spectral, so this is actually really related to frequency. A spectrum, spectrum. So those things is actually referring to a frequency plot, a frequency plot. And we will do, if you look at this diagram, this is Z plane, this orange box. So where does we do this? So we are doing that only to the filter. See this one, but the blue, so it is on all the three things. The input, so we have this blue box. Output, so we have this blue box. Filter, we have this blue box. And it has a different reason why we need to do the analysis. But that this orange box, the exact domain analysis, actually we only do that for filter. Because what we check, we are checking stability and causality. And stability and causality, it is actually properties for system. So what is this? So this is our system, the filter. Input, system, output. Okay, so we don't check stability and causality for input and output. Okay, we need to be very clear on that. So that's why we doesn't have impulse response for inputs. We doesn't have impulse response for outputs. Impulse response is actually representing the system, which is on the filter. But spectral analysis, we will do on all the three things. So for input, so why do we need it? Before we go deep into a week by week looking at this analysis, so but we need to know this first. So why we do spectral analysis on input signal? So actually it is to identify frequency of the noise or the unwanted signal. Okay, so we have the signal, so we can analyze it. So we can identify where is the noise. So because when we know where is the noise, so then we can start design our filter to remove that noise. Okay, so maybe it is a noise, maybe unwanted signal. Unwanted signal doesn't mean it is a noise. So it can be something. So some application needs to separate signal. Okay, so that's what we call an unwanted signal. So that's from the inputs. And then on the output, so we need to check which frequency have been attenuated. So let's say we want to remove a certain frequency from, let's say, 20 kilohertz up to 25 kilohertz. And then we run filtering. And then checking on the output. So how effective is actually our filter in removing that frequency from 20K up to 25 kilohertz? So is it 100% remove? Is it maybe just half of it remove? Or maybe just at 20K, 100% remove. But at 24 to 25K, so we still have a half of the frequency. So that's why we need to check the things and the output signal. So because this is the results. After you do that, you need to check your results. Okay, so one input to identify the frequency of the noise. The outputs, so just to check whether the filtering is effective. And this one, the filter, we need to do that also because we need to know, we need to understand the filter. What is actually this filter do? So we know that we want to remove 20K up to 25K. So is this filter doing that? So we need to analyze that. So on to do that, so we do the spectral analysis here. So this is where we're going to check the passband and stopband frequency. Okay. I hope you guys are still remember what is a passband and stopband frequency. So if not, we're going to look into that again later, not this week, later, right? Check the transition bandwidth and ripple, and then what else? So we have check phase distortion. So we're going to discuss this one by one later. Okay, so because these are the things in the filter, so we need to check. We know what to remove. We need to design how to remove that. Okay, so this is the analysis. And then after that, we're going to check at the output, are we having an effective system? Right, and everything is done on the spectral analysis. Okay, all right. Any questions so far? Okay, and then the rest of the chapter will be on designing. So those are the two design. And then we also have here the yellow box again, because this one will help you in your assignment. The yellow box are actually the MATLAB function for each of the process. Okay, because we have a I think a 5 items, 5 expert group. So you will know, you will need to know which one is yours. Okay, you should know. You need to pick one of it. And maybe this is not enough. Maybe you found other functions for your assignment. Okay, all right. So let's get back. Actually, we have, let's see. So if you look into this class notes, it's actually week 7. So this is a week 7. So there is a spectrum representation of discrete time signal. So actually, this is just an introduction to a spectrum. Introduction to spectrum. So I'm going to skip most of the content in this topic. So that's why I'm straight going to this topic, which is M08, discrete time Fourier transform. But while introducing this chapter, so actually I'm giving you some content from here. So if you notice, so now our topic is a discrete time Fourier transform. So I'm skipping the slides for this one, number 7. Okay. So, but actually I'm covering both. I'm covering both chapter. So this week and next week. Okay, so this is a discrete time Fourier transform. So because what we have, what we already know here is we need to do a spectral analysis. We need to do that because we want to identify frequency of the noise. We want to design the filter. We want to know how effective is our system, and everything. This thing is actually on a frequency, and to get that frequency, we need to do what we call a Fourier transform. Okay. And this is new, discrete time Fourier transform, because the previous courses, what you have learned is on, there are 2 things. Fourier series. The other one is just a Fourier transform. Okay, actually, this is from your previous courses. So one from a signal and system, and you also learn it from, I think, engineering maths. So actually, you have 2 courses previously discussing on these 2, Fourier series and Fourier transform. And if you look at the title now, it is a discrete time Fourier transform. Okay, this one is actually for continuous time. Fourier series is also for continuous time. We're not going to do a Fourier series here, so we're going to do a Fourier transform on the discrete time. Okay, so that's actually what we do is, again, this is a repeating a title, but in a discrete version. Okay, because and everything becomes easier because we're not going to do the integration anymore. Everything is just a summation. But of course, still involving some maths. So you need to strengthen your maths. So that's especially trigonometry. Especially trigonometry. Okay, then if your trigonometry is quite strong, you won't have any problem. Okay, because that's the basic. And we'll see why trigonometry. Okay, why it is a trigonometry which is very important in this Fourier transform. Okay, so we have seen that spectral, and spectral is actually referring to frequency. Okay, it is actually referring to frequency. So first thing that we need to learn is we need to know what is actually frequency. Okay, what is frequency? Anyone can describe what is a frequency?
The rate of something happening per second.
Correct. Exactly. Yes. Okay. What is the unit?
Hertz.
Hertz. You already mentioned about second. So this is actually the unit is 1/second. Okay, so that 1/second is we call it hertz. So that's a frequency. Frequency is something when it is repeating. So there's a repeating pattern, and then what is the period of that repeating? Then we measure that. Then we measure, and most of our signal actually repeating. Vibration is repeating. Even the ECG signal, we can see that the beats per minute, beats per second. Okay, it's repeating. So this is where many of the signal is actually have a frequency because it is repeating. It is a repeating. So that's why frequency is very, very important. And people have modeled it. People have modeled a signal so that it is related to frequency. So that any signal can be represented by frequency. So because of this frequency, then one signal which can represent the frequency is actually the basic signal is the sinusoidal signal. Right? So we have a sinusoidal signal. So this is where the trigonometry comes in. Okay, and what is it? So we have a cosine and sine signal. Okay. So if you're not very strong in trigonometry, so please do a lot of revision on trigonometry. Okay. And so we can say that xt, let's say we are taking a cos, and normally we put it such this, 2 pi f t plus phase. What is it? Frequency. One signal which a basic signal that we can represent frequency is actually sinusoidal signal. Okay, so that's why we learn a lot on this thing. We learn a lot on this thing because signal we can represent it using frequency. Okay, so then how does this looks like? Let's say this is one example. It is a cos 2 pi ft plus pi, and what is every so and this is, oops, can I reverse that? If we look one by one, because this is very important because this is the basic of our signal. This is the time in second. And if you look into this signal, I'm using a continuous time. Okay, we not even touch the discrete time yet. So this is other things that you have learned before. T is a time, and this is the frequency. And I'm going to be very specific now. This is not just a frequency. This frequency has a name. We call it physical frequency. Why we call it a physical frequency? Because this is the frequency that we have physically. When you have a signal physically, so this is the frequency. Okay, and today we're going to look at on another 4 types of frequency. And this is just the original. Because when we want to analyze a spectrum, so first thing that you need to know is, so you should know different type of frequency. Okay, if not, you'll not be able to read the plots. Because the plot can be on capital F, it can be on another 4 types of frequency. So that's supposed to be the first step, understanding the frequency itself. Okay, so, and what is this? Anyone know? Anyone remember? Not know. You all already know it. Have you? Do you remember? What is this?
Is it time shift?
Time shift. Yes, you can call that. Okay. Yes, you can call time delay also. It's also correct. Or you can call it phase. Okay. all of these things are related. Time shift, phase, it is related. Why I'm saying that it is related? It is related because it is not exactly the same. So, but it is totally related. Okay, that one. And what else that we have? So we have this thing. So why we have this thing? We already have frequency, so we already have the time, and then we know that sometimes the signal is delayed. Okay, and we have already represented by phase. And what is this? What is this? Can anyone tell us what is why do we need this 2 pi? Have you ever wondered that you always write this kind of thing, cos 2 pi ft plus phi? We know this is frequency, but why do we need this? Anyone? That 2 pi, what is that 2 pi?
That's 360 degrees.
360 degree, yes, yes. That's
So it
correct.
becomes a
That's
multiple. I don't know.
angular frequency. That's correct. Okay, angular frequency. Because why we need angular? This is actually angular. 2 pi is an angular representation. Why we need an angular representation? Because actually our signal, to show that it is actually repeating. It is repeating from 0 degree, go to 90 degree, 180 degree, and then lastly 360 degree, repeat. Okay, so that's it. That is actually represented by 2 pi. And then after 2 pi, it's repeat and then goes back to 3 pi, not 3 pi, 4 pi. You repeat again. So that's actually that's the repetition. So that cause we use this as the repetition. The 2 pi is the angular representation. So this is where if f is the frequency, the physical frequency f, then we will have capital omega. So this is what we call angular frequency. Okay, because it is in a circular form, so that's why we call it angular. When you combine it with f, so then we call it angular frequency, and this is actually represented by capital omega. We call this a capital omega, and so this is where we can write this, simplify it. Just using the omega. Now it makes sense. Okay, so we have a frequency according to the time, and then somehow it is delayed. Okay, so that's all that we have. So actually we just have a frequency, and this is actually what we call the angular frequency. And f alone, we call it physical frequency. Right, so that's why now we have a name. So we need to know this name. So physical frequency, angular frequency. Okay, then, so how many frequency we already know? 2 frequency. One is a physical frequency, another one is an angular frequency. So we have 3 more frequencies. So we have 3 more frequencies. Okay, so continuous time. So what we have is the f and omega. Physical frequency, angular frequency. But we're not focusing on continuous time. So what we're going to learn in this course is the discrete time. So what we have, so we should analyze everything in a discrete time. Continuous time, we are referring to time in second. Okay, I'm going to put this, this is t in second. continuous time. And now we have n, and n is actually doesn't have a unit because it is a sample. So what is the unit of sample? There's no unit. Just the first sample, second sample, third sample, fourth sample until infinity sample. Okay, or maybe you can go up to a negative infinity sample. Time, you have a unit, second. And no, because this is just integer. So for discrete time, if this is using a capital letter, so actually you're going to see these two. This is another frequency. This is angular frequency. If this is angular frequency, this is also angular frequency. Angular frequency for continuous time. This is angular frequency for discrete time. And from continuous time to discrete time, so what we do is sampling. Okay, so actually we are doing sampling. So let's get back to our signal, basic signal. Why everything we are looking into cos or sine? Because a cos and sine is a sinusoidal signal which represent a basic signal to frequency. Because cos and sine has one single frequency. Okay, so that's the best that we have because it represents one frequency. Because we need to analyze the frequency. Okay. Okay, let's put this back 2 pi f t plus phase. And then do sampling. So what is a sampling? Sampling is, so we have seen that t is actually equals to n over fs. So what is the fs? Fs is frequency sampling. So this is, frequency sampling. So very simple relationship. So what is t? T is just n over fs. So when we do sampling, so we need to replace this t. So replace the t equals to n over fs because we doesn't want the t anymore. So we want the n. Okay. So now our xn, see now we change from t into n. So this one becomes a cos 2 pi f. Then we need to change this, the t. T is actually equals to n over fs plus the phase. Okay. So now let's see what happened to the frequency. What happened to the frequency? And we can write this cos 2 pi f over fs of n plus phase. Okay, so there is no t anymore. Now we are representing our signal with n, but representing it with n, so we have additional term, which is fs. So now we have the frequency sampling. And this one is actually 2 pi small f. Okay, so where the f is actually f over fs. Okay, so that's why in discrete time, so we doesn't have the capital F anymore. So we are using the small f. Okay, so and this is called, sometimes it is called normalized frequency. And sometimes it is called a frequency ratio. Either one. Why it is called a normalized frequency? Because the range is from 0 to 1. This f. When you see this term normalized anywhere, not only DSP. Okay, this is actually maths. This is a maths term. When it is normal, when you see normalized, so actually the range is from range is 0 to 1. Okay, because this f, the range is from 0 to 1 because we do f divided by fs. So then we call it normalized frequency. So now we have this. Okay, what is the unit? Can you guys try to look carefully into this equation, f equals to f over fs. So what will be the unit for this small f? Do some maths here. One, this is quite a simple maths. So what will be the unit for small f? So we know that the unit for capital F is hertz. So what is the unit for this one? No unit. Yes, true, because this is hertz, and this is also hertz. Okay, because this is divides. So that is also why we call it a frequency ratio. It is a ratio. It is a ratio. So there is no unit to it. So F doesn't have a unit. Range is 0 to 1. Okay, so this is where later when we read a frequency plot, sometimes when we use this small f, you won't see any hertz reading. You will just see a value of 0 to 1. And that is actually representing frequency. So that's why we need to know this type of frequency. Okay, and then so we can summarize this also, becomes omega n plus phase. Similar to what we did to the capital F. You multiply by 2f, you get an angular frequency. And that angular frequency is capital angular frequency. This is capital omega. This is not W. This is small omega. Okay, this is small omega. Capital F, physical frequency. Small f, this is normalized frequency. This is angular frequency. And actually the unit is radian per second. Because angular, it is measured in radian. Of course, it can be measured by degree also, not a problem. But commonly, we put it as a radian because pi is radian. Okay, 0, and then you have a 3.142 radian, those kind of things, right? Per second. But this one, this is because this f doesn't have a unit. So what is this? This is hertz. This one, no unit. No unit. And because this is, we just remove the s. So this is actually, it has a unit, which is, the unit is because this is still angular. This radian. What is the difference? This is a radian per second. And this is just radian. Okay. 4 frequency. So now we already know 4 frequency. This is physical frequency, angular frequency of radian per second. This is hertz. And then in discrete time signal, so we have a normalized frequency. So it doesn't have this physical frequency anymore because we need to cover the frequency sampling. So it becomes a frequency ratio or normalized frequency. And then our angular frequency becomes, the unit becomes just radian because this is no units. So then it becomes radian. Okay, for frequency. The last one before we stop for today. Okay, let me reprise this. So this is a continuous time and continuous frequency. Because the frequency, this f can be 1 hertz, 1.2 hertz, 1.3 hertz. It can be 20.0001 hertz. So that's what we call a continuous frequency because the value is a continuous. This one. This is on discrete time. Discrete time. But the f, if you remember here, what is the range? The range is 0 to 1. This is not discrete. What is discrete? Value must be integer. If this is an integer, so you just have 2 values only. So not possible, okay? Not logical. So actually this frequency and this frequency, the normalized frequency and the angular frequency in radian. So those frequency is actually continuous frequency. It is a continuous frequency for discrete time. This one, continuous frequency for continuous time. So now we have two things now, time and frequency. Looking at our equation here, so we have two things also, time and frequency. Okay, and because we should have in our digital system, everything's supposed to be discrete. Everything's supposed to be discrete. So actually this is not practical on our this f and omega, small omega. It's not practical on our digital system, because our digital system only accept a discrete value. Okay, so this is where we have another one. It doesn't have any space now. So we have another one, so I'm going to put it here. Another frequency, we call it K. What is K? K is a discrete frequency. Okay, so this is actually the final frequency that we need. Means that this is actually the frequency that we are actually analyzing, implementing on our PC. This is actually the frequency. Not this one, not this one, not this one, not this one. Originally, it is from this one. Processing is actually this one. Theoretically, we do this. Okay, so this is actually just on theory. Implementing is this key. So this is what we call a discrete frequency. So we're going to do a sampling. Sampling the frequency. To get a discrete time, you do sampling on time. To get a discrete frequency, you do sampling on the frequency. Okay, so that's all the 5 frequency that we need to know. Because later when we do analysis, when you do a spectrum plotting, you will see all these 5. You will see all these 5. And now you already know that what are these frequencies. Okay, from physical frequency, the one that which we have, and then some representation, because we are actually representing a repeating signal, right? So we have angular, and then convert it into a discrete time. So we have a representation of a discrete time. It's a small f, and this a small omega. And lastly, so this is the actual frequency that we implement in our PC, or any of your digital system. Okay, so that's actually the journey to have the implementation. Okay, so we will stop here next week. So we're going to look at all this formula from Z transform into a Fourier transform. Okay, and then we will look on some example on it, and then look on the plot itself. Because when we do analysis, we need to look at the plot. We need to look at the plot. Then we do analysis. Okay, because that's our main purpose here. Why we do Fourier transform? So we need to get that frequency analysis. We need to get that one. Okay, any questions before we stop? All right, assuming no no questions. So okay, so that's all for today. So see you guys back next week on not next week. Next week is a semester break. So another 2 weeks from now. Okay, bye everybody. Assalamualaikum warahmatullahi wabarakatuh, and still a good morning.
Thank you so much, Doctor.